All right, in this video, we're going to introduce logarithmic functions. We'll be looking at calculating logarithmic values. This video, we're just going to introduce logarithms, and in the next one, we'll look at some examples. So we looked at exponential functions in previous videos, and the inverse of the exponential function, which, again, as a reminder, our exponential functions are in the form b to the x, where b is a positive real number that is not equal to 1. But the inverse of an exponential function is called the logarithmic function. So it's denoted our inverse function as log base b of x. So whatever the base for our exponential function is, that'll also be the base that we use for our logarithmic function. And what logarithms do is they allow you to, if you know what this value is here, what the exponential function is equal to, it'll help you determine what power you have to raise that base to in order to get that result. So we do have some special bases for logarithms. Again, keeping in mind that the bases will be positive bases not equal to 1, just like bases for exponential functions. But the common logarithm is a log with a base of 10. So just like our counting system is base 10, powers of 10, like tens place, hundreds place, thousands place, the common logarithm of a real number x is denoted log base 10 of x. And we usually do not write the base of 10 when we mean base 10. So if you see log of x, for our purposes, that means log base 10. Now, in some older textbooks, this has a different meaning, but for our purposes, if you see logarithms without a base written down there, it's assumed to be base 10, also known as the common logarithm. The other base is called the natural logarithm, and that's log base e. So in our exponential functions series, we took a look at the value of e, that it's about 2.718. And we have log base e of x called the natural logarithm, and we write that ln of x. The reason why we don't use nl is because typically, just like written here, this lowercase l looks like a 1, and it's just used to avoid confusion. So instead of it looking like, let's say, n1x, it's lnx. That's a natural logarithm, and it's a log with a base of e. Some old textbooks still use log base e, and oftentimes in other courses, if you see log of x, it's assumed to be log base e. But in this one, anytime we have log base e, we're going to write that as the natural log of x, or ln x. So here we have in blue the graph of log base b of x, where our base is greater than 1. And we have the exponential function b to the x in red. Notice also, again, that reflection across the y equals x line for a function and its inverse, that the graph in blue is a reflection across this y equals x line of the graph in red, and vice versa. Likewise, if our base is between 0 and 1, with our red graph here, that's exponential decay. With our logarithmic graph, notice again it is a reflection of this red graph across this diagonal y equals x line. So anytime we have an inverse function, its graph is a reflection of the original graph across y equals x. So some properties of our logarithms. The domain of a logarithm is positive real numbers only, so from 0 to infinity with a parenthesis in front of the 0. So whether we are looking at this graph or we're looking at this one, all of our x values are 0 or higher. So in other words, there is a vertical asymptote for the y-axis, or x equals 0, for these blue logarithmic functions. Our range, our output values, is all real numbers. So once again, we have a new function that has a domain restriction to it, and that's the logarithmic function. Whatever we're taking the logarithm of must be greater than 0. So our domain of logarithmic functions is going to be greater than 0. The 0.10 is on the graph of our logarithmic function, and x equals 0, the y-axis, is a vertical asymptote. So we have an x-intercept at 1, and the y-axis, or x equals 0, is in fact a vertical asymptote. So again, remember the behavior of the graph around a vertical asymptote. It's either going to go up forever or down forever, but never actually hit that vertical asymptote itself. Log base b of x is 1 to 1, which means it has an inverse and passes the horizontal line test. It is continuous, so we can draw it without lifting our pencil off the paper, and it's smooth. There are no jagged, sharp edges to it. In terms of the relationship between exponential functions and logarithmic functions, we have b to the a power equals c if and only if log base b of c equals a. So in other words, the base of your exponential expression, in this case we're using b, the base of this exponential expression is the same as the base of the logarithmic expression. If you take the base of the logarithmic expression b and raise it to this power, b to the a power, you'll get what you're taking the logarithm of. So in other words, as I mentioned earlier, logarithms help you figure out, if you know what this value is here on the right and you know what your base value is, they help you figure out what exponent, what power you have to raise that base to in order to get that result. So you just take log base b of the result, and that'll tell you what the power is. So in other words, log base b of c is the exponent you get when you in order to raise b to get to c. So we have also log base b of b to the x equals x for all values of x. And another property that we have is b to the log base b of x equals x, assuming that x is greater than 0. Because again, this log base b of x in this exponent here, this value of x has to still be in the domain. So we can only take logarithms of positive numbers. For our log base b of x, when we have a base that's larger than 1, our function is always increasing. It is known as logarithmic growth if it's increasing. The limit as x approaches 0 from the right, so that's what this notation means. This little plus sign that looks like 0 to the plus power means as we hit or get closer to 0 from the right, our y values are sinking down forever towards negative infinity. And as we go to infinity, our y values are going up to infinity. So this means coming in to getting closer to 0 from the right, our y values keep going down forever. As we go to the right, as x approaches infinity, our y values go up forever. They just don't go up very fast. For log base b of x, when our base is between 0 and 1, our function is decreasing. That's called logarithmic decay. Much like we have exponential growth and exponential decay, we have the same with logarithmic. And this time, the limit as x approaches 0 from the right of our function is going to be infinity. So as we get closer to 0 from the right, our y values keep going up and up and up. As we go to the right on the graph, as x approaches infinity, our y values get closer to negative infinity. So we have that for when the base is between 0 and 1. All right, so that about does it for this video. In the next one, we're going to take a look at some examples of logarithmic functions. So